So first thing which comes to our mind, there have been a lot of emphasis on this term called artificial intelligence. So let's first try to understand that what is artificial intelligence on a very high level and why we may need it in first place for solving a problem. So let's try to understand with an example. A person goes to a doctor and he wants to get checked at whether he got diabetes or not. And what doctor would say is, okay, there's some tests which you need to get done, and based on the test results, doctor would have a look, and from his experience, from his studies and previous examples, the patients he had seen, he would be able to evaluate the reports and say that the patient has diabetes or not. So if you just take a step back and think, I said that doctor has experience. So what do we mean by experience? The doctor has learned what are the characteristics of somebody having diabetes. Will it be possible if we can provide this experience in the form of data to a machine and let machine take this decision whether a person has diabetes or not? So the experience which doctor learned through his studies and his practice, what we are doing is we are taking customers' data who have with different reports and different parameters on different things like the glucose count in blood or the weight and height and all these parameters about a human being. And based on that, we have fed it to a machine and tell that what are the characteristics of a person who has diabetes. And from this, let's say we have 1 million customers data we have given to a machine, and let machine do the stuff from his experience, which comes from the data or historical data to be precise, and do the same task which a doctor is doing. So what we have done is, if you see from this example what an artificial machine or artificial intelligent machine is doing, that it's learning from the historical data and trying to do the same thing which an experienced and intelligent doctor was doing. So this kind of area or domain activities which human beings were doing, if we can make machine intelligent enough to do the same task, why we should create these artificial intelligence based machine systems on a very high level. There may be a lot of points, but if we just discuss a few points, that human beings have limited computational power, and we guys may be good in terms of classifying things, like, you know, you can see your friend in a group photograph and easily can say who is your friend and who are others. You can easily listen to a language and comprehend what a person is doing. But human beings are not very good in doing a lot of mathematical. If you try doing good amount of mathematical computations in your head, probably it will not be very easy. And second is that it's not possible for human beings to work continuously, let's say 24/7 a day for 30 days continuously. If we can make machine do such stuff, one, they would be able to kind of do these computations very fast. And like we spent a good amount of time in discussing the GPUs. And I also mentioned that Google is talking about a TPU machine, transfer processing units, which would be hugely changing the entire paradigm of computations, and machine would become more and more competitive or even better than human beings in some of the fields. This is the formal definition, but if I loosely translate, it's basically that artificial intelligence machines are those machines which can do tasks which human beings can easily do. So things like identifying what's written, let's say in a license plate, or playing games. And I'm sure some of you would already heard that machine have defeated the Go champion and the chess players. Now we have digital agents like Siri and others which can understand what we want them to do and can take intelligent decisions from the text or from the voice itself. Basically, these are very high level, and some of the fields where deep learning has made a great inroads. Something like game playing, expert systems, self-driving cars, robotics, natural language processing. So there may be different and new areas where we are implementing. All of you know that every experience of human beings is getting digitalized. The kind of things you buy, kind of things you watch, and what your preferences are, who do you like on Facebook, who you don't like, what kind of movies you like, and all these things in terms of reviews being captured online. So once your data is going and captured online, there are systems which can analyze this data. So given this huge data generation, as well as now we have machines which can process it and make some intelligent decisions are available. So that's why you will see there have been a lot of emphasis now in last couple of years. A lot of new things are coming in. Some of you who have been reading these papers on different subjects, different architectures would know that most of these architectures are not very old. It's a very dynamic field every day. In fact, on a weekly basis, you will be hearing about a new API or a new kind of architecture being developed by somebody. Most of the stuff we will be studying in these classes are not very old. like convolution neural network and recurrent neural network, some of their variants are as new as last year. If you guys follow TensorFlow closely, they introduced a library called object identification. Object identification, object detection API, which TensorFlow has made available for everybody. You would be able to see it yourself that this API works. There are 5 different options of selecting different deep learning architectures or convolution neural networks for this API. But it's been able to identify human beings and all other 90 objects there with almost 99% accuracy. In some cases, from even human beings would be finding it difficult to kind of see and predict what the object is. But this machine has gone even beyond a human capability in terms of identifying objects. Given that we have a fair understanding or very high level understanding, we haven't gotten into details of artificial intelligence, but basically from a loose understanding that artificial intelligence of making decisions or machine making decisions which human beings were earlier doing the task, something like game playing and natural language and drivings of car. Let's understand how this machine learning and deep learning are related to artificial intelligence. Given this learning that now your machine is able to understand and learn from the data, we can solve multiple business problems with the help of this. So let's take a very small example. It was like whether a person has diabetes or not. And I was mentioning that this kind of decision being taken by the doctor based on the reports he has got. And these reports have some numbers, like number of time a patient had a particular kind of issues, or what is the glucose count and what is BMI and what the person's age. And based on these numbers, the doctor was able to make this kind of decision. We can take the same analogy where we were trying to predict which species of flower it is. We can take information of patients and different attributes on different features of a report and the patient, and the machine would be able to learn from these data sets, and for a new customer or a new patient, it would be able to classify whether the patient has diabetes or not. So there are 2 sections of it. First one is the information about the patient and different characteristics of his health. So from this, which is number of time and glucose count till age, these are the information points about the patient. And the last column is the information whether the patient has diabetes or not. This kind of problem where we have some information points where they explain what the situation is, and other in the last column, or the information of output is in some kind of classes. There is a specific type of machine learning problem it is. But as of now, the characteristic is that we have some information about the patient, and the last column is telling me whether the patient has diabetes or not. So what your machine basically learns that it learns all those rules in the example which I was quoting, that earlier cases people used to create these hand-coded rules to predict whether an event will happen or not. But in machine learning, your algorithm will learn from the historical data and see what are the combinations which decide whether a patient has diabetes or not. And these combinations would be of something of this type. It is only for illustration. It's not the real numbers, but it's for illustration that your machine or your machine learning algorithm is being able to identify these rules based on the historical data. So after learning, it has created the glucose count is less than 99.5. If yes, then go to next one. If no, the person does not have diabetes. If glucose count is greater than 166.5, yes, the person has diabetes. And if no, then there are further drill down of rules. So all these combinations or rules are dynamic in nature. And what I mean is that these rules would be changing if your data set changes. And you can take the same model, can do the work whether a patient has diabetes or not, and you can take the same model and make it learn on a new data set, let's say flower species, it would be able to learn the new rule from itself. So the intuition, like human beings were learning from examples, your machine learning algorithms also learn from examples. But just to frame our problem statement, that machine learning, we know it learned by experiences and from the data from the historical events. There are 3 kind of problems which may be interested in solving. First one is called a supervised learning problem, and supervised learning problem is basically occurs when you have some input variables and one output column. So both the examples which we discussed till now, one was on the flower species where we are taking data on different features of a flower and then which species of flower it was. So the last column is the dependent variable or output variable we are trying to predict. And all the information variables are called input features or input variables. So input features or input variables, it's kind of interchangeably being used in different texts. Input and output, these are the two different sections of supervised learning. Why it is called supervised learning? Another take, if I need to explain it, that we have a column to guide the algorithm whether it's making the correct decisions or not. So let's say your model says the person has diabetes, but the actual data says the person does not have diabetes. So you have some kind of correction mechanism within your data itself, which can help your model tune itself to make better predictions. So this kind of output variable, some texts it's also been called a teacher variable. So it's guiding the algorithm to decide those rules which I just go through. Another type of machine learning is called unsupervised learning. And in unsupervised learning, we have only the input features. And our objective is that we should be able to identify the patterns within the data itself. So some of you who are working in telecom domain or marketing campaigns, you would be very much familiar with segmentation analysis or cluster analysis, where our objective is to identify coherent groups within the larger population. We take the customers as it is the whole population, and based on different parameters and variables, we identify some of the groups of customers or products, whichever the business problem is, to identify which are similar in nature so that we can take either marketing campaign or develop new products for those specific groups. Final is called a reinforcement learning. A reinforcement learning is a kind of learning where the agent learns from the environment. So it works kind of reward and penalty. You can think of a self-flying helicopter. So you leave it in the environment and it will be deciding based on the wind speed and other parameters in the environment that how much it should fly. And the reward is that the fuel should be efficiently be spent and more time it should be spending in the environment. So supervised learning, as I said, that the objective here is that we have some input features, and input features would be holding information about different aspects of a given problem or customers. And we have an output variable which would be explaining whether the event happened or not, some kind of output variable. So there are two types within supervised learning. One is called as regression, second is classification. And the differentiation happens only because of the type of output column. If your output column is the type of numerical values or continuous values like numbers, so that would be a regression kind of problem, a very high intuition level. For example, you're working on a problem where you need to predict how much would be the sale of your company given the information that how much they're spending on marketing, how many employees are working, which month it is of the year. And if you have this information, you are going to predict what is the $1 million of sales your company would be doing. So these kind of problems where your output variable is of numerical values, then it's a regression problem. On the other hand, if the dependent variable is of categorical nature or of discrete values, it signifies that it's a classification problem. Given that it's a categorical values, your objective is that how you can put the different customers or products into different classes. So that's why the name suggests classification problem. So as I said, there are two kinds of supervised learning problems. One is regression, another one is classification. So let's take a use case where we need to predict the housing price of a particular locality. And we have information about these houses on different parameters. And these parameters are like these. So let's say, what is the crime rate in that area? How old is the home? The distance is how far it is from the city. This is from Boston housing data. So this is, if I'm not wrong, it's percentage of black population or some variable. We have the description later on. And what is the actual price of the home? And all these features from crime to ISTAT is the information about the house. So these are my input features. And the output feature is the price of the house. This is in $1 million. And our objective is that we should be able to fit an algorithm that it should be able to learn from all the historical homes which were sold based on all the features and what was the price it was sold for. And once the model is trained, it should be able to predict that how much should be the price for a given home. Let's take an example. Let's say one of you is interested in buying a home in the Boston area, and you would like to know that what is the ballpark figure for a 2-bedroom flat, which is of some square feet and let's say 20 miles from a specific location. What should be the price? So one way would be you go and talk to people and try to understand that what has been the average price. Or if you have this kind of algorithm available which can help you understand that given these features, that was the price, and if you can create a regression model, it would be able to help you that given some features of the new home which you are interested in buying, what should be the price of it. So as I said, there are two sections. One is the independent variables, all these information about the home, and the last variable is dependent variable, which would be information about what was the price. You see this is a kind of scatter plot between the distance from the city and price for the home, keeping all other variables constant. We are not looking at the influence of other features, but we are looking if we just need to model or if we need to find a relationship between the distance from the city and what is the price. From this graph, you can make out that further the city house is, the lower the price would be if we keep all other things constant. So here it's like if we can identify this kind of relationship, which is called linear regression, but for a given distance from the city, you would be able to predict what should be the ballpark figure for a house if you just have this information, not all other information which we have talked about. In a similar fashion, how it's been done is that there would be a relationship between the price of the house and all the features which we discussed. So this is only a relationship between one of the variables, distance to the city, and the price of the home. In a similar fashion, we would be able to find relationship between the price and all other features. So all other features, if you know, like how old is the home, how big it is, what is the crime rate and all. So this kind of model is called a regression model, and it's a very basic equation of a straight line. Y here is called the dependent variable, A is intercept, and B is called slope, and X is called independent variable. If we go deeper and try to understand what it's basically doing is, this equation is trying to tell me that if I already know the relationship, if I know the value of A and B from my historical data, which is about different homes, given the value of X, I should be able to calculate the Y. Y in our particular example is price of the home. Let me try give an example what slope means. So slope is the change in dependent variable if we change X, which is the independent variable, by 1 unit. So let's say if I change X by 1 unit, how much change in happen in Y? Help me understand what is the kind of relationship between X and Y. And A is the value which tells the value of Y when the X is 0. And you can think of it something like that: if you put the value of X equal to 0, whatever the value is Y, then that's the intercept. But basically from an intuition perspective, you can think that an intercept is the value which is there even though you don't have any information about X. For example, we were discussing the relationship between the distance from the city and the housing price. Even though the house is exactly in the city, then there would be some value, and even though the house is 100 miles from the city, there would still be some price. So it helps us kind of intuitionally understand the relationship. It also helps the line to understand where it starts, whether it starts from the origin or some place within your axis. And this kind of equation is called equation of linear regression, because if you see here the power of X is 1, and so that's why it's linear in nature. And it is also that we are fitting the relationship between X and only one of the variables. Multiple regression, where what we do is that instead of finding the relationship between only one variable and the dependent variable, in most of the practical scenarios, the dependent variable Y is dependent on more than one features. So for an example, your house price is dependent on all these features, all these information points available, and all you want is that your regression model would be able to identify a relationship giving all the information together and then predict what is the price. The equation becomes Y equal to B1x1, B2x2, or B3x3, this kind of equation, where B, B1, B2, B3, and all these coefficients help us understand that what is the contribution of a single or of a given variable into your regression equation. So let's have a look at how you can fit this model in Python. So if you look at the first block of the code where we are saying import panda as pen pd, import numpy as np, and import matplotlib as plt, this is the convention in Python to import some of the libraries which we would be using. So these are the libraries which are required for running this module or this regression model. So once we import these, all the functions available in these libraries, we can call them very easily. And we will be seeing that how you can call them. So once you have imported these libraries, if you see that we are loading the data called Boston, and that this is the same data set which we have been discussing in terms of a use case here. So next line of code. So here we are importing the data and loading the Boston data set. The next line of code, we are calling the pandas library because we have imported the pandas library as PD. Then we are calling a function called data frame so that we can create a data frame in Python, and we were creating it boston.data. So it will be creating boss as a data frame. So data frame, on a very loose term, you can think of kind of spreadsheet kind of format where your data is being put in rows and columns, and you can think of an Excel file kind of framework for a data frame, though it will be different, but just for intuition purpose. And after importing, I am calling dot head. So what dot head does, it will be giving top 10 rows of my data set. So there are all the 13 columns. In Python, index start from 0. You can see that index started from 0, 1, 2, 3. So you can see what this data is. This line of command which says dot columns. So dot column gives you all the features available in your data set. So these are the different feature names. So these are the different column names for the data and the price. In the end of the code, I have written actually one line of code which can give you all the details, that what the target variable is, what was the history of data, where it was recorded and all. So you can easily look at this. We are calling this boston.target and we are calling it as a boss.price. So we are creating a column in our data frame which was boss from boston.target. So there is another data vector available in the Boston data set itself. And now specifically we are saying y is equal to this particular variable. Y we will be representing our dependent variable. All the features plus the Boston price. So boss.drop price x is equal to 1. It means that we have dropped the price variable from the overall data frame, and x is 1 specify that we are removing the column. So x is 0 represent the row level operations in Python, and x is 1 represent the column level operations. Print statement, we are just printing now the x. So this x is all the input features of our data set. So all these columns which we will be using for predicting the housing price. And how it will be working, so it's not an actual model, but what actually happening is once we have created the model, it will be doing that, it will be fitting a line which would be going through the actual data set, would be something like this, that price is equal to some intercept term plus b1 multiplied by crime, b2 multiplied by another variable zn, then b3 multiplied by another variable, and so on and so forth. And this intercept and b1, b2 and bn would be the coefficient which your model would be learning from your already available data. And here we are showcasing top 5 values of our housing price. So y is the dependent variable, and we are looking at what is the top 5 values. So this was only a very brief and very basic introduction, that how do you import our data, how you can see what are the different columns. It has nothing to do with machine learning, but it is only for people who are new to Python and for people who have been out of touch in Python, if you just want to brush up skills. And this line of code, if you have a look, which I'm highlighting now, we are using a scikit-learn model for test, train, and split. And what it's doing is for both, because we have already x and y, the test sizes we are saying 0.33. So it's basically we are randomly selecting 33% of the data we are putting it separate in the test bucket so that we can test it later on. And this random state 5 means because we'll be randomly selecting, if you specify a random state, every time you run this code, you will be selecting the same set of elements from your data set. It helps you understand that the variation, if you run the code multiple times by changing, the variation is not coming because of the selection of sample. It should be because of the different model changes you are making. This dot shape function in Python specify that what is the dimensions And if I mention the first one, xtrain.shape is giving me 339 and 13. Basically, it's telling me that there are 339 rows and 13 columns in the data set. X-test, there are 167 rows and 13 columns. And your Y-test is just 339 rows and there's just one column, or it's just one vector. The number of rows in X-train and Y-train are same, and X-test and Y-test, the number of rows are same because they have been selected for the same combination. So same houses, we have selected the input features as well as the corresponding values of output, and same has been done for the test section. What we are doing here, as I was saying, that we have imported a library called scikit-learn, and scikit-learn has different modules for different machine learning algorithms, and linear regression is one of the modules in scikit-learn. So we can call this scikit-learn module from linear regression called LM, and this equal to in Python is called assignment variable. So we are assigning LM as a linear regression module in the scikit-learn. And now what we are doing is, if you look at this line only, lm.fit, so basically we are telling that use the linear regression module from scikit-learn and fit the model between xtrain and ytrain. So basically what we are telling the model that you learn those coefficients for different x values given y values in the training data set. Basically what the fit function does, it calculates the values of your intercept, B1, B2, B3 for all the features in your input features for a given y variable. So once we have fit in the model, and once that has been fit, we can use the same model for doing the predictions. So let me remove it. It should be like this. So lm.fit, we have fit in the model. And once that has been fit, we can use the learned model, which is LM, with a function called predict xtrain. So what it will be doing is, once it has learned those coefficients, B intercept and B1, B2, B3 for all the features in input, you can use the predict function for making the predictions for your training data set. And you already have actual values as ytrain, and then you can compare that how good your model is doing. And how you can compare it, that if you look that we are put together same thing we have used for the x-test data set, lm.predict x-test, and again the prediction has been done. So if you see here, I have put together as a data frame y-test and y-test bread, and the difference look like this. For the first value, which was 37.6, and the actual value was 37 point this value. Then the predicted value this, actual value is this. And this difference between the actual value and the predicted value signifies that how much is the error in your data set. So had it been that your model is giving the same prediction as it was the actual value, you would say there is no error, your model is 100% accurate and all the predictions being made by the model is absolutely bang on. But normally it doesn't happen. You end up having predictions which are a bit off from the actual value, and we measure the difference as one of the characteristics or one of the parameters to identify how correct your model is. In this particular statistic, there are two metrics being used for identifying, but the most basic one used is called mean squared errors. And what mean squared error is, it is basically the difference between actual value and the predicted value by the model. And what I mean by this is that let's say this is your predicted value 37.6 and this is your actual value. What you do is you take the difference of these two and then take the square of it. Why we take the square of it? Because this, in some values the difference may be negative or positive, and if you sum it up the difference may come to 0, and you may end up thinking that okay, model is doing really good stuff. To avoid it, what we do is that we take the square of it so that the difference between actual and the predicted becomes positive, and you can sum it up to showcase that how far your predicted values are from the actual value. And then you take a mean of it to showcase that what is the mean difference between the actual value and the predicted value. It can also be used for model comparisons. Here I can show you that how it is working. That let's say you have some actual values, something like this, and let's say you fit a model, I fit a model. So there is one model prediction 1, another model is prediction 2. So what you can do is you can take the difference between the actual and the predict. So 10 minus 2 is 2, and then you take the square of it, which is 4. 23 and 21, again 2, square of 2, 4. Then third one, the difference is 5, and then square of it is 25, and so forth for all the values. You get the total value of sum of squared errors, and you divide it by the number of inputs, which is 5, and you get the mean of the squared errors. And you do the same thing for the second one, and if you see it is very less, 5, so probably it would be able to help you understand that which model is doing a better job in terms of predicting the housing prices or any other numerical variable. And there is another statistic which has been used for identifying how good your model is, which is called mean absolute percentage error. And that's basically the absolute difference between the actual value and the predicted value, absolute terms. And you sum it up all the values for all the entries and divide it by number of all the value of absolute value of your actual values. And it can help you understand that what is the average percentage your predicted values are different from the actual values. So sometime if you see, it will be somewhere in percentages. So what I've done is I've taken the absolute difference between this value and the predictions. I sum it up and divide it by the sum of my input values. So whatever value comes in, you can say, okay, it's 5%. So it will be fair to say that your model is 5% off from the actual values, or the error term in your model is, let's say, 5% or 6%. And whatever predictions you're making from the model, you can keep a buffer of that percentage when you share it with the team. And what I mean is that, let's say your mean absolute percentage error is around 10%, and it's about the sales of a company. So when you share this forecast, you say that my predictions are around 90% accurate. They may be actual sales, maybe plus minus 10%. So this can help you giving this kind of variability in your predictions. However, you have implemented code in Python itself or the scikit-learn library, you can call mean squared error, the function from sklearn, and it can help you calculate the MSC for a given model. So basically, there was a very quick introduction to linear regression. Though there are different applications, but one thing remains common, that we are trying to predict the dependent variable whose nature or the type of dependent variable is numerical or continuous data. Some of the applications like predicting life expectancy based on these features like eating patterns, medications, disease, etc. You can predict housing price. We have already seen the example on that. We can predict the weight on different features like sex, weight, prior information about parents and all. And you can also predict the crop yield of crop based on different parameters like rainfall and all. And as I said, this is like very limited use case list. I'm sure people who are working with sales department, you have to make predictions. How much would be the sales? People who are working with call centers, you need to predict what would be the number of calls for next month. People who are working with marketing, you need to predict what would be the footfall in a given company or a mall. So there are different applications of regression models, but one thing is common across all these applications is that the dependent variable which we are trying to forecast is of continuous data type. So let's get moving to the next agenda for logistic regression. So at the time of the introduction to machine learning, we discussed there are two kinds of supervised learning techniques. One is regression and other one is classification. And the major differentiating factor between the two were that in regression, we held a dependent variable of continuous values, and in classification problems, we had a dependent variable of categorical types. So let's take an example of how we can do it. So here, let's take a use case where we have got some information about some customers, and the data set looks like this, that we have some customer ID or user IDs, gender of the customer or the user, his or her age, estimated salary every month, so you can think of in any one of the currency, either INR or dollars, and whether this user purchased an SUV or not. So as I was saying earlier, the dependent variable here is 0 and 1. So it's a discrete value or categorical value, which we need to predict. And the features which we'll be using in the model are age and estimation. Why we would need a logistic regression kind of algorithm? It would be a straightforward process that if I take purchase as a numerical value 0 and 1, and I take some input features like age and estimated salary. And you will be right in saying to some extent that this is a possibility of doing it. So there are two major problems coming if we follow this, and some of you can help me. What may be the problems if I try using the linear regression for solving this kind of problem? But one limitation I can think of is that here I'm looking for an output which can give me some kind of probability that how likely I am to buy a product or service. So one thing, the limitation or the restriction with probability is that the probability term should be between 0 and 1. And 0 signifies that there is no probability or there is no likelihood of event happening. And 1 means that it's certain that the event will happen. There is no possibility that we can have probability values less than 0 or greater than 1. So if I'm fitting a linear model taking the purchased column as my dependent variable, my values, because the linear regression has no such limitations, can pass these values beyond 1 or less than 0. So what I require is that I fit the model in the similar fashion like I did the linear regression, the equation I used earlier. Then I want that information would be coming from my features in the similar fashion. But what I want actually is that this y should be mapped to the values between 0 and 1. And given the limitation we have just talked about probability, that it should be between 0 and 1, it should not go beyond 1 and less than 0, I need to find ways if I can kind of force fit or kind of force this y value, which would be coming from this equation, and I force fit into values between 0 and 1. So to solve this problem, there was a function called sigmoid activation function, which would be extensively be used in our deep learning as well at different places. But logistic regression comes from this activation function itself, which is a function looks something like this, that output value would be 1 divided by 1 plus e to the power minus x. And x is not actually the one of the input, but any value we are giving it. And if you fit any value into this particular equation, it can convert any value between minus infinity to plus infinity. It will map it to between 0 and 1. If your value of x, which you are putting in here, I could have selected a different value, different name at least. But if you give the highly negative value, the output would be very, very close to 0. If this input is positive, then the output would be close to 1. If the value of x, the input here, becomes 0, what would be the output? 1 by 2. Because any values power 0 is equal to 1, and 1 divided by 1 plus 1 would be equal to 1 by 2 or 0.5. So logistic regression is nothing but an extension of your linear regression itself, with one additional fact that you want to force fit your output between 0 and 1. And for that, you are using activation function called sigmoid activation function, or sometimes it's also been called logistic activation function, to do the same task. So this is an intuition behind your logistic regression, where you take values of your equation from intercept and different coefficients for your input, and you map these outputs between 0 and 1. So once we have understood that logistic regression is nothing but the extension of your linear regression only, with a restriction on the output being mapped between 0 and 1, we are shifting. Had we were fitting the regression equation, we would be having scenarios where the value would be going beyond 1 or less than 0. And to avoid this scenario, we fit in logistic regression with the help of sigmoid activation function, which looks like this. And if you see, as I was saying, when your value of your model go beyond, let's say this is R0. So all the values which are positive and greater than 0, the curve goes and tangential towards 1. And for all the values which are less than 0, it goes towards 0. And at the place of 0, the probability is 0.5. So it's a 50% probability if your output is very much close to 0 or it's 0. It can be used for multiple scenarios. One of the example we are taking is the example whether somebody will buy an SUV or not. But if you're trying to solve problems like somebody will say yes or no to a product or service, or whether something is true or false, or high-low, or any different categories. But logistic regression can easily be put in for multi-class classification problems. And basically, if I just give you a very quick introduction, how it works is that in multi-class classifications, it kind of does mapping that one class versus rest of the other classes. And then same analogy follows, that which class a particular event would be associated with. But end of the day, for whichever class or category the probability is highest, the model will predict that it should be belong to that particular class. Like MSC, we have a statistic or a parameter to evaluate how good your model is doing. And that was a parameter to check that what is the difference between the actual value and the predicted value. And how we were doing it, we were taking the value which was actual, subtracting the predicted value, taking square of it, do it for all the examples and divide it by number of training examples we have. And then it gives you some number. And I was also saying that this number is helpful in kind of comparing different models. So let's say you fit a model, I fit a model, and we compare MSC for both of them. Whichever model is giving me a lesser MSC, it is kind of an indication that probably your model is doing a better job in terms of prediction than mine. In a similar fashion, we needed a kind of a statistic to see how good your model is doing when your model is doing a classification problem. So here there are 4 categories that, let's say we have only 2 classes, good and bad. Actual values good and bad, and what your model is predicting good and bad. So 4 examples which belong to good category and your model is also predicting them good category. So this type of events or examples are called true positives because your model is doing correct prediction on positive examples. Another category, which is your actual value for those examples is bad, they belong to bad category, and your model is also predicting them bad. These are called true negatives. And these are correct predictions because whatever the actual value is, your model is also predicting the same thing. However, there are 2 categories where your actual value was bad, but your model is predicting good. These kind of examples are called false positive because your model is falsely predicting them. These are good examples. And another category or last category is called false negative, where actual value were good and your model is predicting bad. So how do you learn, or how does your model say that which model is doing good job? So what we do is we calculate what is the percentage of values examples have been predicted correctly. These sections in blue, true positive and true negatives, these are the examples which your model has been able to predict correctly. And these 2 groups, false positive and false negative, are the incorrect predictions. So what we do is we just want to take what is the percentage of correct predictions, and this metric is also called confusion metric. Let's say there are some examples out of which 65 examples were there where actually they were good category examples and your model is also predicting them as good class, good category examples. 44 are those where they belong to the bad category and your model is also predicting them bad. This is 44. And 8 are actual bad and prediction is good, and 4 are actually good and predicted bad. What you do is you sum up all the correct examples, 64 and 44, and divided it by all the examples in your data set, all correct and incorrect ones. And here you get 89%. So all you can say that your model is being able to predict 89% accurately. Or if you want to explain it to your business team and say that whenever I give you a prediction that 100 customers will churn, and I give you a list of 100 customers, I can say with certainty that at least 89 will churn from them with some certainty. So because your model has given you 89% accuracy. So that's how it's been kind of communicated to business teams, that we are thinking that our model is 99% accurate and whatever prediction we are giving, we are very, very certain. But if your model accuracy is 70 or 60%, then when you give the predictions to a business team, you say that, okay, though we are giving you the predictions, but we are not very certain whether it will work correctly or not. So this accuracy percentages in a similar fashion like we did for linear regression as MSC to identify how good the predictions are. Your accuracy percentage is another metric to see how close or how correct the predictions has been. So now we can see the implementation of logistic regression in Python. So first few lines, if you see, we are importing the libraries or the machine learning libraries which we require to do the data manipulations. We are importing the data, which is a CSV format, and this data is already available on your LMS. If you want to import, you can easily import from the LMS itself. Unlike the Boston dataset, which we were importing from the library itself, here we have got a flat file as social network ads.csv, and you can call a read_csv function of pandas library to import the data. So you are importing the data as dataset, and as I said, head showcase the top 5 rows of your data. So here we have only 5 columns. One is user ID, gender, age, and salary, and the last column is our dependent variable, which signifies whether a customer or a user bought the SUV or not. So it's 0 and 1, and 1 means the person bought. In the previous code, we used one convention of selecting X and Y. Here we are showcasing another way of selecting, that's called iLock. So we are looking for the location, and this convention, if I go through what we are doing here, that this is the dataset. Within the dataset, we are specifying the locations. This colon means that we want all the rows. And as I was saying earlier, that in Python, the index start from 0. So what we are saying, we want column 2 and 3. So what we mean that this is 0, this is 1, this is 2 and 3. So we want as our input features 2 and 3 and the values. So it will be creating an array of these 2 columns. We could have used gender, but I will leave it to you that first we need to create the gender as a vector of 0 and 1. So you can create a function which will say, okay, if gender is equal to male, then 1, else 0. Or you can create dummy variables. There are functions available in scikit-learn. So it's an exercise for you that this is the code already available, but I would encourage that if you can also include gender information into your model. The next line of code, why we are saying the dependent variable, is all the rows and column number 4. So column number 4 is your purchase information, whether a customer bought the SUV or not, and again the values to convert into a kind of list format. So we have specified 2 things. The 2 columns is the information about the input features or the information about the user in terms of how much money they make and what their age is, and information of Y, whether a customer bought the SUV or not. And the next line, we are doing the train and test split for the same stuff to evaluate whether the predictions being made by the model on the training dataset on which the model was learned is still doing the correct classification on the dataset or the test dataset which was not involved at the time of training. And this 0.25 means that we are selecting 25% of the data for test and remaining 75% for our train. What is the correct split of train and test? Normally it is correct to choose between something like 60-40 or 70-30 or 80-20. If your data set is big enough, then I think having 80-20 kind of split is good, or whatever. You can try these different combinations, but as a rule of thumb, most of the time I have seen people taking something like 60-40 or 70-30 kind of distribution between actual value and the predicted value. Now there is one important thing for data pre-processing, and this selection which I have made for doing the data pre-processing, and some of you who come from the machine learning background will already know that how important it is to kind of scale your data. And what do I mean by scaling? That if you look at the data set which we are using for input, one is the age column and second one is the income column. Age can be somewhere between, let's say, 1 to 100 or 120 at max, and your income is in like some thousand and some 100,000 numbers. Both these values are on different scale. Scaling your data on, let's say, all the values between 0 and 1 will help me understand that what is the importance of each variable. For example, if you look at a regression equation and you see those coefficient B1, B2 for all the input features, these coefficients can give you kind of indication that how important a particular variable is. But this intuition will only be correct if all my features were on the same scale. If these features like age and salary, when they are on different scales, you will not be able to compare what these coefficients really mean because they are 2 different scale your values come from. So it is always a good idea to have all your features on the same scale. There are multiple ways of doing it and there are multiple type of scaling parameters. The simplest one is called min-max standardization, and what does it mean is that for a given column, let's say we are talking about age column, which is 1935-26, if I need to do min-max standardization, what do I mean is that I take the value it is, let's say 19, and minimum value here is, let's say 19, I have only these 5 values. So how it works is that this is the formula, this is the value, or how it's been presented, xi minus the minimum value of the column, so let's say age, divided by max of age minus minimum of range as well. But basically what this formula will do, if I do it for all the values in the age column, it will be converting all the values between 0 and 1. And there are other ways. I also said that there are normalization process, which is like you take the value minus the average value, divide by the standard deviation, if I call it correctly. So whichever method we apply, all I'm saying is that these values of age and salary should be brought to the same scale. So if I'm applying this min-max standardization, I'll apply to both my columns so that both these variables are on the same scale, and I should be able to use them in my model. And this is again a very important thing, that whenever you do standardization, you will be using this process that you fit the normalization or standard scalar on the trained dataset, and you use the same learned standardization from the train on the test dataset. But basically how it helps, that your dataset on which your model is being trained, it will be converting the values between 0 and 1 based on the minimum and maximum values. If the test dataset have different minimum and maximum values, it can have different value for the same number. So that's why the process is that we make our standardization fit on the training dataset and use the same minimum and maximum value for test normalization as well. It gives the same scale for all the values, and for model predictions it's very helpful. In a similar fashion, like we called a linear regression object from scikit-learn in the previous example, in exact same way, we can call a logistic regression function from the scikit-learn. So it's a scikit-learn linear model, and we are importing logistic regression. Now we are fitting the logistic regression between X train and Y train the same way we did it earlier for the linear regression. And once it has been fit, we can do the prediction for test dataset. We are also doing the same thing, that we are calling the function which was classifier for the logistic regression, and we are doing it on the X test dataset. And here the default probability is 0.5. So what your algorithm is doing in the back end, for all the examples wherever the probability in X test became greater than 0.5, it was tagged as 1, and for all the examples where probability was less than or equal to 0.5, it was tagged as 0. And now we are calling this function called confusion matrix between y-test and y-pred. So we are comparing that what is the values of your true positive, true negative, false positive, and false negative. So this is the values, that these are the true positive, these are true negative, and these are the misclassification values. And if you want to calculate the accuracy, you can easily do it by 65 plus 24 divided by 65 plus 24 plus 8 plus 3. So all we are doing is we are trying to identify what is the percentage of correctly predicted numbers, and this is the code of section. So it can do the prediction. If you see what it has done, basically if you look at the section, that your regression model has fit this line, and you can see it's a straight line, and that is why in some of the text logistic regression is also being called a linear classifier. And why it is called linear classifier? Because it is predominantly being made for fitting a linear equation. The logistic regression equation was y equal to a plus b1x1 b2x2 and all these coefficients and respective inputs, but the highest power of your inputs were 1, and you would already know that if it's a polynomial of power 1, it stands for a straight line. So that's why you can see a straight line. There are ways, some of you would argue that we can fit a nonlinear line with the help of logistic regression, but you would also concede that there are some tricks which we use for creating nonlinear lines through logistic regression. For example, you introduce higher order polynomials into your model so that the separation becomes nonlinear. These kind of algorithms are really helpful only solving the problems when the objects are linearly separable. When the separation between the objects is not linearly separable, these kind of algorithms are not very helpful. And we need to identify algorithms which can fit in nonlinear hypothesis or separation boundaries between different classes. So let's take a use case to understand that what are the simple scenarios where unsupervised learning can be used and how does it really work. So let's take an example that we have some housing data, and housing data in terms that what their locations are, and these white dots on the screen in the blue background showcase that where these homes are located. And the objective of education officer is that he needs to find a few locations where the schools can be set up. And the constraint is that students don't have to travel much. So given this constraint in mind, the officer needs to decide the location. They may be easily we can identify if we are not using any algorithm. So let's say if I know that I'm an officer, I need to open 3 schools in the locality and I know the information where the homes are located, I can easily see, okay, probably this is one location. I'm just highlighting it. And the constraint I also mentioned that students don't have to travel much. What I mean is that if you open the school here, then everybody of you would say that it's not a great location for a school given that it's far away from the population. So this is not the correct location. And from the perspective of identifying the home, probably these 3 from a human intervention or like some of you has been given the task without any algorithm, you can decide that if you set up the school, most of the students would be traveling less to go to school. So given this problem, we can easily see that we don't have a dependent variable as such, which is telling us whether it's the correct location or not. All we're doing is that we have a number of locations which we need to find schools for, and then we have home locations, and based on the distance of each home, we need to identify which will be the proper distance, proper locations of these schools. And another thing which is coming from the same logic that there are no predefined classes of these locations. And one more point if you would like to add, and some of you who have done the clustering or the segmentation job in your respective works, that these numbers, we say 3 or 4 or 5, it's not predefined. It is most of the time given by the business that how many clusters or segments they would be looking for. Though there are statistical ways of identifying that which is the best number of clusters should be, but basically most of the time it would be coming from somebody in the business that, okay, I see that, let's say I was working for one of the Indian telecom companies here quite a time back, and at that time their subscriber base was around 300 million customers. And imagine that if you're trying to create segments for this bigger population, and if you create 3 or 4 clusters, you can easily understand that it would be very difficult for marketing team or any product team to design products for such a big population. So though statistically it may look that, okay, 4 or 5 unique segments are there, but you end up creating a lot of small segments, and there may be a possibility that you will be creating 20 or 30 segments for such a big population. So my intent of saying this number that we are trying to identify 3 locations within the population has to be decided either by business or people like you who have knowledge about the data, as well as that what kind of business they are running and what is the final usage of this segmentation exercise. So let's see, one way of doing or selection of these school locations is like we have already doing it. If you identify that somebody looked at the homes and see the densities where the density is high and selected the home automatically. But there are algorithms also available to do the task. And I can give the name here itself. It's K means algorithm. And so first we would like to understand that how does an algorithm work if it needs to identify which is the best location. So if you are looking at my screen, let's say our objective is that we need to identify 2 locations first, and we have some data and its scatter plot available, and we need to identify where the school should be so that the distance from home should be minimum, if that's our objective. So how we can do it, that let's say we randomly assign 2 points from the existing data set. And actually easiest way is that you randomly pick 2 numbers from your data set itself. And then what you do is you assign these 2 selected points as these are your cluster centroids. So this is the center of your selected population. And in the second step, so once you have initialized these 2 random points, then the next step is that you measure the distance of all the homes from the initial selected point. So let's say you do the distance of this home from this selected point and again from this. That for each house from these randomly initialized point, you measure the distance from the selected point or the initialized point and any home location and see which distance is minimum or which distance is less in comparison to the other from the selected initial point. So we can easily see that this distance is smaller than this distance, and this point would be assigned to this particular group. The first initialization step is initialize as many number of centroid, as many clusters you need. And in the second step, you do the cluster assignment. And in cluster assignment, how it's been done is that you measure the distance from these initialized points and see wherever the distance is minimum, and then assign this home to that particular segment or cluster. So this exercise has been done for each home. I'm just trying to show for a couple of them. And based on the distance, the assignment is complete. So this color also signifies what we have done is after measuring the distance for each home from the initial points, we have assigned these points to this cluster and these blue points to second cluster. And then once this assignment is complete, it moves the centroid. So what we'll be doing is it'll be taking the center of all the selected points and then it will move the centroid from the previous point to the next point based on the new assignment which has already been completed. And then what's been done is the same exercise which was done earlier in terms of cluster assignment, that we measure the distance of each home from the centroid. So distance from this centroid and wherever it's minimum, assign it to that particular cluster. And this process has been repeated again for both the centroid. And once the distance has been measured on the improved or changed centroid, again the assignment process has been started. So once you have moved and then measure the distance, and then assignment also changes like it was done in the previous step. And we continue this process till the time we have reached a location or a point where this change in assignment have stopped completely. So once we have reached this kind of place or this kind of scenario where as many time you measure the distance from the centroid to the different points, your centroid does not change. This exercise or this point is called that your model has converged, and at that point you can say, okay, these all group, there is one group of these points or these homes. So this is one cluster and second one is this cluster. So this is how k-means work. It has wide variety of applications. There is a function available in scikit-learn library. You can try implement it. The intent of showcasing you this example of unsupervised learning was that we will be having two algorithms which come from unsupervised learning section of machine learning. And these would be your restricted Boltzmann machines and autoencoders, which work on a similar methodology of unsupervised learning. So in a similar fashion, like we started discussing in the beginning, that where should be the location of these schools, we can use a k-means algorithm and initialize 3 points randomly and do this distance measure to each home and assign the homes to a cluster wherever the distance is minimum. And we continue this process of measuring the distance and assigning it to the cluster till the time these values have been converged. The most important task for any data scientist is not to remember which library is required or what are the codes. In my understanding, the most important thing which data scientists should remember is that once you've been given a business problem, first you should be able to understand that what kind of problem it is, whether it's a problem of supervised learning or it's an unsupervised learning. Given it's a supervised learning problem, whether it falls into the regression type or a logistic regression type, if you can make these decisions, then for implementing the algorithm, you will find a lot of help. In fact, scikit-learn would have initial codes for almost every algorithm. So you don't have to remember line of code and algorithms. All you should be able to do is once a problem is being given to you, you should be able to identify what kind of problem it is. Most of the time in unsupervised learning and specifically in k-means kind of models, we use this elbow method as an indicator or help you understand that what is probably a number we should start with for starting the final implementation of your model. So let me give you an intuition. How does it work? SSD stands for sum of squared errors. And what it means is actually, if I go back a little, that suppose you have identified these two clusters. So sum of squared error would be that you take the centroid and measure the distance for the points which are associated with this cluster. So you measure the distance for each point in the orange group and sum square all the distances, and the same exercise being done for the blue points. And whatever the total number comes in after doing this exercise, you will be getting what is the total number of squared errors. And if you have two clusters, you would have some number. And just for intuition, I'm saying that this total sum of a square is coming as 100. And that's only for intuition and example. I'm taking this number to help you. Let's say there was one more cluster somebody identified here. And all these 3 points, though it's blue in color, but I'm saying all these 3 points belong to this particular segment. and rest of these points remained same as it was previously. And as we saw with two clusters, our sum of square was coming as 100. When we have three, you can see that these points are a bit far off from this particular cluster. So if I'll be doing it with three clusters, this distance would be a bit less, given that now I have a point which is closer to these points, and whatever error or distance these 3 points were adding, it would be a bit less given the cluster was here. And let's say this distance goes down to 95. I'm just making up some numbers. So probably what it's telling me that sum of squared is going down, and probably I'm finding clusters which are closer or more closer to the actual data points. And as you would know that if I'll be increasing the number of clusters in the population, this distance would be going down hopefully. And this distance can go up to 0 when every point become a cluster itself. So if let's say I have 20 data points there, and I assign that every point is a cluster in itself, then just measuring the distance from the point, which would be 0, and overall SSD will become 0. So it may start from a very high number, but it will be reducing with each cluster point or cluster you will be adding to your data. So this line, which is sometimes being called the elbow method, what it's actually showing you, so if you had one cluster only anywhere in the population and you do some of the squared distances, this was the distance. When you had two clusters, this was the distance. When you had three, these were the distance. When you had four, this was the distance. But when you had five, the sum of squared error did not reduce much. So if you see, it's like very less. And after that, even though you keep on adding different clusters, the sum of squared errors is not going down. So as I was saying, this process or this method is kind of indicative method, and it gives you an intuition that if I have done it, my cluster analysis with different number of clusters, and I'm measuring the sum of squared errors for given number of clusters, and I see that after 4 the sum of squared error is not going down, it gives me an intuition that probably I have found clusters which are more or less coherent and the population is not very much away from the centroid. From the point, you can make it an assumption that probably 4 clusters is a good idea for my given population. But as I also mentioned, that it is just an indicative process. It's a good starting point, but you need to see that how the distribution of your clusters look like, whether they solve the business problem you're trying to solve or not, and if not, whether you need to further divide the clusters which your initial model has identified. And here we'll be taking very quick introduction to a third type of learning, which is called reinforcement learning. What it actually is, we have seen from the two learning types, the supervised learning and unsupervised learning. The first one was that we were trying to predict some dependent variable. In the second one, we are trying to identify some kind of structure in the data set, or if I put it into other words, that we are trying to identify some kind of coherent groups in the population. Third one is reinforcement learning, and it's basically that an object or a system learns from the environment, and there is no right or wrong answer given to the system explicitly or in the beginning itself, like in the case of supervised learning. Here, the object would be moving in the environment, self-flying helicopters, where they fly on its own and they take the decision that what is the wind speed and what is the pressure around it, and they correct their procedure accordingly, and the objective they need to achieve is that they need to fly for a longer period of time. So here we are given an example. Let's say we have a robotic dog and somebody needs to train it to take correct decisions, and correct things would be that it walking on the path where people needs to walk, and it's not going down from the path, and if some task is being given, it's working correctly. So there are two components of reinforcement learning, which is called reward and penalty. If the object or the system does the correct thing, it receives some reward in terms of mathematical things. Obviously, we will be providing everything in terms of mathematical numbers. And if it does the wrong thing, it receives the penalty. And basis this thing, it will keep on taking its decisions. So like a dog, if it's walking correctly, it receives the points. Like ball is being thrown, if the robotic dogs go and pick it up, it's a reward point. If it doesn't do the correct thing, it receives a penalty. So most of all these reinforcement learning agents working in a similar fashion. Some of you who are interested in implementing it, there is an algorithm called DeepQ. It's an algorithm where you can design your own system and you can assign what are the rewards and penalty. Similar fashion, reinforcement learning is also interacting with the space, as I mentioned. So self-driving car is also one of the examples. which would be receiving rewards and penalties based on whether it's running on the track, taking the right turns, and moving at the correct speed, maintaining distance from other cars which are running. So reinforcement learning has a huge implementation or requirement for self-driving cars, or some of the components of it, not all. Some of the components also in self-driving car are supervised learning, for the point that car needs to understand what the objects are in front of it and all other objects identification. So what are the real limitations of machine learning, given that we already have all three types of algorithms, supervised, unsupervised, and reinforcement learning algorithm already available? Then why we want a new architecture or new type of algorithms for our artificial intelligence systems? First and foremost is the dimensions. And when I say dimension, it's like the type of data we get from a lot of sources. Let's say we receive images, which is grid-like image. So where the pixels and what is the strength of pixels in the image. Natural language processing, so language data comes in a different length, and the work is also different in the sense that suppose you need to design a machine learning algorithm which can do language translation. And if you conceptualize this idea of language translation from a machine learning algorithm perspective, your inputs become a sequence of words and your output is also sequence of words. And some of you who are working in machine learning algorithm, try thinking that whether we have any algorithm currently available, like logistic regression or decision tree, which can help me even fit the algorithm or fit the problem. Leave aside how good the accuracy would be and all, but these problems which come from a different type of data source and we trying to solve a different kind of problem, like language translation or chatbot kind of problem where you give a sequence and it returns you a sequence. So these kind of architecture is already not available in machine learning. So that is one of the reasons that we need to identify some algorithms which can deal with such data sets like images and languages. And second, it can also fit different kind of models which are not only for predicting or classifying, but also give you some kind of values like sequence I take an example of. So that is one of the reasons. First, we are looking for a different type of architecture for solving such problems. Then second problem, which machine learning algorithms are not very good in dealing, is the dimensionality. So we would have seen with a size of, let's say, 1,000 variables and let's say 100,000 rows and 1,000 columns, probably you can still fit some of the machine learning algorithms on top of it. But given the kind of problems we are dealing with, like images, every image, let's say it's 200 by 200, means 200 pixel by 200 pixel, and it's a colored image, it means there are 3 channels. If you do the maths, 200 multiplied by 200, let's say this is your image and it's 200 by 200 because every image is kind of a matrix only. And if it's a colored image, actually colored image are being represented in system through 3 channels, red, green and blue. So there would be 3 such grids, but one top of the other. So number of pixels you need to have to represent your image in the system or in your algorithm would be 200 by 200 by 3. And then you calculate how many features it would be. If my math is correct, it should be like 120,000 features. So even a simple image of such small dimensions, you end up getting 120,000 features. And plus, if you're really working on a complex problem solving in terms of, let's say, an object identification in the images, there may be 5 or 6 objects which you need to identify and you're dealing with, let's say, 100,000 images. Then your scale of data becomes so huge for any machine learning algorithm to easily handle it. And your machine learning algorithms fail in terms of getting any interesting results out of it. So coming to solution part, that we need an architecture which can not only read such data in terms of images, but it is capable enough of dealing with such huge dimensions of data. So this is the second benefit which comes from the deep learning algorithms, and we'll be discussing how do they manage such high dimensional data when we go and talk about different architectures. And third and the most important reason that we will be looking for a different kind of model structure or different kind of algorithm is for identifying the features. So in machine learning algorithms, we as data scientists spend a lot of time in kind of curating the important features. Either first you'll be scaling the features, and after scaling you'll be creating the interaction variables, then you'll be creating, if the separator is not very clear, then you need to introduce high dimensional data. Let's say it's your data point. And if you see that line you're fitting is not separating clearly, then some of you would be trying the higher order polynomials of your input features. So all such things which not only difficult to come up, there is a lot of trial and error that which kind of transformation and which kind of variable creation. So what kind of variable will really work for classification problem? That's first thing. And second is, if you're working on higher order polynomials, what is the correct order of polynomial I need to create it? And just to give you the scale of it, let's say you are dealing with only 100 features, and you need to create second order polynomial with interaction of all these 100 features, then you will end up getting around 5,000 features from the second order polynomial only. If you want to get third order polynomial like cube variables or the interaction of 3 variables together, then these 100 variables will come around 170,000 features. So this creation of features is very, very difficult. If we go and start creating these features on our own, and our objective, let's say, to identify a television in the image, and we have some pictures where we need to identify, even though you have created those features manually, and some of you who are working in the field of computer science for quite some time would know that earlier we used to use features like SIFT, SIFT, HAR features, and HOG features. But these are like kind of static features for a given object. But we may argue that this television is there in this picture here, but in other picture it can be somewhere else. So the feature which I'm identifying, it has to be spatial indifference, that it can be anywhere in the image. And same goes for language, that if you're dealing with language data, it should be not only able to understand the meaning of word or how does the word fit into the sentence, but should also be able to understand that what is the context of each word. But these word embeddings, neural network, help you understand it, what are the related word to a given word, and from that you make predictions. So these broad problems of machine learning algorithms, one is they are not being able to play with or deal with different type of data like images and natural language. Second is the dimensional problem, if the dimensionality goes in like 100,000 features and all. And third is this feature creation on its own. So these are the 3 basic reasons that one of you or all of you would be interested in going to one of the deep learning architecture for solving such problems. And fourth, if I may add it, that all the deep learning architectures, given that we are putting a lot of computational powers in them, they end up giving you a better accuracy both for classification and regression problems. So that's the fourth benefit. And how does it really work? There are different stages in a deep learning, and why they are called deep? Because it's not just input and output like we have seen in regression, that you have a y and x is some kind of linear equation. Here we have different intermediate field, but there are a lot of intermediary field for doing such complex calculations, so that all these features which I mentioned, that suppose you need to identify a television, all such features get calculated at different stages, one after the other, and final stage you have very, very refined features. Not only for image, we are taking the image classification, but any problem we are trying to solve, through the multiple stages, your model would be able to learn these intelligent features which are really important for your classification or regression or any such problem which we are trying to solve. So these were the few benefits for deep learning, and these are actually the broad reasons that somebody would be interested in learning the deep learning algorithms.
Now let us understand this with an example. So we'll take an image which has 4 pixels. So if you can notice, we have 4 pixels here, among which the top 2 pixels are bright, that is, they are black in color, whereas the bottom 2 pixels are white. Now what happens, we'll divide these pixels and we'll send these pixels to each and every node. So for that we need 4 nodes. So this particular pixel will go to this node, it will go to this node, this pixel will go to this node, and finally this pixel will go to this particular node that I'm highlighting with my cursor. Now what happens, we provide them random weights. So these white lines actually represent the positive weights and these black lines represents the negative weights. Now this particular brightness, when we display high brightness, we'll consider it as negative. Now what happens, when you see the next output or the next hidden layer, it will be provided with the input with this particular layer. So this will provide an input with positive weight to this particular node, and the second input will come from this particular node. Since both of them are positive, so we'll get this kind of a node. Similarly, this node as well. Now when I talk about these 2 nodes, the first node over here, so this is getting input from this node as well as from this node. Now over here we have a negative weight. So because of that, the value will be negative, and we have represented that with black color. Similarly, over here as well, we are getting one input from here which has a negative weight, and the another input from here which again has a negative weight. So accordingly, we get again a negative value here. So these two becomes black in color. Now, if we notice what will happen next, we'll provide one input here, which will be negative and a positive weight, which will be again negative. And this will be also negative and a positive weight. So that will again come out to be negative. So that is why we have got this kind of a structure. If you notice this is nothing but the inverse of this particular image. When I talk about this node over here, we are getting the negative value with a positive weight, which is negative, and a negative value with a negative weight, which is positive. So we are getting something which is positive here. Now, obviously, I want this particular image to get inverse. I want these black strips to come up. So what I'll do, I'll actually calculate the inverse by providing a negative weight like this. So over here, I've provided a negative weight, it'll come up. So when I provide a positive weight, so it'll stay wherever it is. After that, it'll detect, and the output you can see will be a horizontal image, not a solid, not a vertical, not a diagonal, but a horizontal. And after that, we are going to calculate the difference between the actual output and the desired output, and we are going to update the weights accordingly. Now, this is just an example, guys. So guys, this is one example of deep learning where what happens, we have images here. We provide these raw data to the first layer, to the input layer. Then what happens, these input layers will determine the patterns of local contrast, or it will fixate those patterns of local contrast, which means that it will differentiate on the basis of colors and luminosity and all those things. So it will differentiate those things. And after that, in the following layer, what will happen, it will determine the face features. It will fixate those face features. So it will form nose, eyes, ears, all those things. Then what will happen, it will accumulate those correct features for the correct face, or you can say that it will fixate those features on the correct face template. So it'll actually determine the faces here, as you can see it over here. And then it'll be sent to the output layer. Now, basically, you can add more hidden layers to solve more complex problem. For example, if I want to find out a particular kind of face, for example, a face which has large eyes or which has light complexion. So I can do that by adding more hidden layers. And I can increase the complexity also at the same time if I want to find which image contains a dog. So for that also I can have one more hidden layer. So as and when hidden layer increases, we are able to solve more and more complex problem. So this is just a general overview of how a deep network looks like. So we have first patterns of local contrast in the first layer. Then what happens, we fixate these patterns of local contrast in order to form the face features such as eyes, nose, ears, etc. And then we accumulate these features for the correct face, and then we determine the image. So this is how a deep learning network, or you can say deep network, looks like. And I'll give you some applications of deep learning. So here are a few applications of deep learning. It can be used in self-driving cars. So you must have heard about self-driving cars. So what happens, it'll capture the images around it, it'll process that huge amount of data, and then it'll decide what action should it take. Should it take left, right, should it stop? So accordingly, it'll decide what action should it take. And that will reduce the amount of accidents that happens every year. Then when we talk about voice control assistants, I'm pretty sure you must have heard about Siri. All the iPhone users know about Siri, right? So you can tell Siri whatever you want to do, it'll search it for you and display for you. Then when we talk about automatic image caption generation, so what happens in this, whatever image that you upload, the algorithm is in such a way that it'll generate the caption accordingly. So for example, if you have say blue colored eyes, so it'll display a blue colored eye caption at the bottom of the image. Now when I talk about automatic machine translation, so we can convert English language into Spanish, similarly Spanish to French. So basically automatic machine translation, you can convert one language to another language with the help of deep learning. And these are just few examples, guys. There are many other examples of deep learning. It can be used in game playing. It can be used in many other things. And let me tell you one very fascinating thing that I've told you in the beginning as well. With the help of deep learning, MIT is trying to predict future. So yeah, I know it is growing exponentially right now, guys. So this is the problem statement, guys. We need to figure out if the banknotes are real or fake. And for that, we'll be using artificial neural networks. And obviously, we need some sort of data in order to train our network. So let us see how the data set looks like. So over here, I've taken a screenshot of the data set with few of the rows. In it, data were extracted from images that were taken from genuine and forged banknote-like specimens. After that, wavelet transform tools were used to extract features from those images. And these are few features that I'm highlighting with my cursor. And the final column or the last column actually represents the label. So basically label tells us to which class that pattern represents, whether that pattern represents a fake note or it represents a real note. Let us discuss these features and labels one by one. So the first feature or the first column is nothing but variance of a wavelet transformed image. The second column is about skewness. The third is curtices of wavelet transformed image. And finally, fourth one is entropy of the image. After that, when I talk about label, which is nothing but my last column, over here, if the value is 1, that means the pattern represents a real node. Whereas when value is 0, that means it represents a fake node. So guys, let's move forward and we'll see what are the various steps involved in order to implement this use case. So over here, we'll first begin by reading the data set that we have. We'll define features and labels. After that, we are going to encode the dependent variable. And what is a dependent variable? It is nothing but your label. Then we are going to divide the data set into two parts, one for training, another for testing. After that, we'll use TensorFlow data structures for holding features, labels, etc. And TensorFlow is nothing but a Python library that is used in order to implement deep learning models, or you can say neural networks. Then we'll write the code in order to implement the model. And once this is done, we will train our model on the training data. We'll calculate the error. Error is nothing but your difference between the model output and the actual output. And we'll try to reduce this error. And once this error becomes minimum, we'll make prediction on the test data and we'll calculate the final accuracy. So guys, let me quickly open my PyCharm and I'll show you how the output looks like. So this is my PyCharm guys. Over here, I've already written the code in order to execute the use case. I'll go ahead and run this and I'll show you the output. So over here, as you can see, with every iteration, the accuracy is increasing. So let me just stop it right here. Alright, till now, any questions, any doubts with respect to what is our use case, what is the data set about,